All right, so today we're going to talk about fields again, just fields in general. Previously, we talked about electric fields and touched on gravitational fields very lightly. But here we're going to cover it, I guess, in a little more detail, mostly just a little review for it, because it is its own topic for HL physics. But you'll find that most of this was stuff that had been covered previously in previous lessons. Uh, so it should pretty much just be a review, but we'll do it nonetheless. Now we'll start with talking about electric fields. So we'll go with electricity first, electric first, and in that we came up with the idea that we could do an electric field because we talked about how anytime we wanted to change our situation, if we change one of the charges out in a group of charges or in a big situation, we have to redo the whole problem. So we came up with essentially what I would describe as just a math trick where we put a little test charge near another big charge, and that little test charge was so small that it really didn't have an effect on the big charge. So we were able to put it there, measure the force on it, and then just divide it back out of our equation and be left with just the charge we're really interested in. The little test charge would normally go here like Q1 and this would be Q2, but now we're left with just that one over R squared. So essentially what we have here is a number that we can use anytime we want to put some other charge near this charge Q here, and we'll put it in here, and then all we'd have to do is take our number, our vector that we already have for that point, multiply it by the new charge we put there, and we'd be done with the problem. And so if we can solve this throughout all space around, giving us a field very similar to a mathematical field where each and every point around this charge Q has its own vector E associated with it, then anywhere we put something, we simply have to look and see what is the value of E at that location, and then multiply it by the charge we put there, and we automatically know the strength of the force that would be acting on that new charge there. We also went from there and we took and we said, okay, well, when we looked at the electric fields, and I didn't expect everybody to really know this at that moment, but we had one of Maxwell's equations that looked like this, and it basically told us that the curl of the electric field was 0, and anytime you have a cross product between two vectors, because this is a vector and this is a vector, and they equal 0, it meant the vectors were parallel, which meant we could replace E in this equation with something that was parallel to del, which would just be this little vector here, times some scalar that just simply scaled it, made it longer or shorter. And at this point we could say then this little scaling amount, this scalar that was here, would be our scalar potential. It's our voltage, we define it as. And we ended up coming up with a couple of equations where we basically said that ultimately what the interpretation of this was that and I'm going to put a little sub E on it to make sure we know it's electric because we're going to do something similar for gravity in just a moment, was that it was essentially our potential energy per charge, or the work to place a charge in that location per unit charge there. And it gave us this scalar potential here. And it was the nice thing was it was a little easier than working with electric fields because electric fields were vectors, and vectors are a bit of a pain, and this is a scalar, so it was easy to go into the voltage world, work the whole problem out with scalars, and then work back to getting your electric field. And you could get your electric field by using the relationship E times D, the distance moved to that electric field, and we would pretty much be done with it. And if we had a gravitational field thing instead, we can do something very similar for gravity. We can basically think back to where I said that that electric charge was essentially equivalent to thinking of it as electric mass. So gravity, very similarly, other than it only being an attractive force and not having a repulsive force like the electric field does, we could come up with our own gravitational field by doing something very similar, by taking our force equation and instead of putting two masses together. We're going to put one big mass, like a planet or a star or something like that, the sun, and then we're going to put a small little test mass here. But we're only going to put it there temporary, long enough to measure the actual strength of the force before we then go ahead and divide it back out and leave it like this. Now, if this is done, what you should notice is all of these things here, they give you a unit of acceleration. So we can actually denote this with a little lowercase g going along with our gravitational acceleration, because this will give you an acceleration. And if you're unclear about that, you just think F equals ma. And so what we had when we started with this was the gravitational force, but then we divided this missing m out of it. And what happens when you divide the m out of F equals ma? You're left with just the acceleration. So the acceleration due to gravity is essentially our gravitational field, and it'll work very similarly. In fact, you can do something similar to this. You can basically make a Maxwell equation divergence law like this, curl law like this, and you can come up with a gravitational potential, which we'll put a little g on to make sure it's different, and it'll also be that same sort of thing, your potential energy or your work to then place a mass in that position, not a charge. And a lot of the same kind of stuff that we had over here, we can just rewrite over here with a little sub g and masses where all the q's were, and of course a big G where that k is. And but it's very similar mathematically, and so so a lot of this should be very familiar, even though we're doing this, and you got to be sure you keep in mind that that is actually acceleration. Now, as we move further and further out away from our charged object, what would happen? So say we had a charged metallic sphere. So we had some sort of sphere here, and it had some sort of charge Q on it. Now, if you remember, charge will reside on the surface, and if that is the case, we can basically build a little graph of the electric field as a function of distance from the center of it, how far out you go from the center. And when you're inside a charged conductor, so this has to be a conductor for this graph to work, a conductor, then all the charge resides on the surface. And while you are inside that sphere, if you are less than the charge, then or less than the radius of the sphere, where you're inside where that sphere charge is, then you basically have an electric field of 0 here to the point of the radius of that sphere. And then at that point, as soon as you cross it, it will jump up to being our maximum before it decays down pretty rapidly on out to infinity. We can do a very similar graph to this for, for gravitational fields, where, I keep doing that, my apologies, where we can have a mass. Now, it's unlikely that we have a hollow planet, so mass will be throughout the entire thing, some mass m, and we can do a similar graph for it where we have our distance from the center, and in here our field strength vertically. That's just awful. My apologies. So we'll have our field strength here, which is just little g. And here it's a little different because out here at r, the radius of the object, it's going to look the same after you pass there. It's going to decay down real fast in a nice smooth curve like this from the 1 over r squared dependence, just like over here it was. But before that, this is not a hollow sphere. The planet has, or the object has, mass throughout all of it. And if we assume it's evenly distributed, then what will happen is you'll get this nice straight line as you go out, and more mass is inside. Basically, as you move further and further out here, there's more mass pulling you back towards the middle, and so that acceleration, that field strength, will increase, unlike over here. Now, what if this wasn't a charge conductor? What if this was something that had an even charge distribution throughout the entire throughout the entire volume of it, so that as you went out, it wasn't that you normally, like it is now when it's a conductor and all the charge is on just the surface. As you move out, you're not there's no more charge being added inside to pull you back down towards the middle, not until you cross that boundary. But if this wasn't that way, if it actually had an even distribution of charge throughout here, then the graph would look just like this one, except this would then be the electric field instead, but its shape would be very similar to that, which hopefully y'all see this is a nice curve, not horrible like I drew it there. It's, you know, this was a little better curve. It would look just like that. It would be the same, just a nice little curve. And you would get that same sort of, you would get a graph that looked just like this with an even charge distribution, but that's not often what you see. Usually it's a charge conductor, so this is the one you need to be aware of the most. Next, we can actually talk about drawing these fields and what they would look like. If you're far away from the object and the object is spherical, then you're going to get field lines that point out radially, or in electric fields they could point out or in, but you would have some sort of sphere or point, and you would have the field lines going like this. I'm not going to put arrows on them because I'm generalizing here to gravity or electricity, and you know, for electricity they could be pointed either way. So, but the field lines would point out like this, and they would diverge. And remember, the separation between the field lines tells you the strength of the field line. So if I look right here close to the object, the lines are that close together, and as I move further away, the lines get spread out more, which indicates to me that this is a weaker field out further and a stronger field up close. And it'd be the same thing with gravity. As you got further and further away from the planet, the field lines would spread out, and it would get weaker and weaker as you got further and further away, which again goes back to our 1 over r squared dependence. I'll show you that one more time. 1 over r squared dependence for both of these things. You get that same similar kind of shape. But what you can also do with this is you don't have to be super far away from the sphere. And as I hope you remember, if you are up close to a sphere, just like we are on Earth all the time, well, we're close to Earth. It's a big circle, big sphere. We're really close to it, and it seems flat to us. So if you are close enough, you can basically get just an approximation that your sphere is flat. You're getting up real close to a tiny little spot on the sphere where it looks flat, just like the Earth looks to us in our pretty much everyday lives, and in which case all these lines coming in, you're real close to them, and they will appear to be parallel. And so you'll have these parallel field lines approximately, as long as you stay close to the surface. You'll have these parallel field lines like this that all just go up perpendicular from the surface, because if you remember, field lines always leave our surface perpendicular to it when you're up real close to it like that. And so these would be leaving perpendicular to our surface, and as long as we stay down real close to them, zoomed way in, we can approximate them for all practical purposes as being perfectly parallel with each other, and it'll allow us to do some approximations with it later on. The next thing, if you remember, we did lines of equipotential around these things, and they basically had to fit the symmetry of what was going on. So we had these equipotential lines, equipotentials, and these lines of equipotential. And around a spherical object or a circular object, they would basically be circles perfectly around it that stayed the same distance away from it the whole time. And everywhere these lines cross a field, they cross it at right angles. I know I didn't draw the most perfect circle, but these are all right angles where it's crossing. And you would have that line of equipotential, and you could have another one out further. And the special thing about these lines of equipotential is you could move along them, move a charge along them, or move a mass along them in the case of gravity, and not have to do any work. No work would be done on it to move it along a line of equipotential, because that's what that means, equipotential, one potential. And if you're not changing potential, then you're not doing work, which you can see in the little equation we wrote here. You know, if this is 0 and the charge isn't 0, then the work has to be 0 in order for the potential to stay the same. I mean, when I say this is 0, I mean the change in this is 0. Then the work done would be the change in energy, and it would have to be 0 as well. For a nice uniform field like this, the equipotential lines have to cross again at a 90-degree angle, so we would just get these straight lines. And that should kind of make sense, because we did problems before where if you didn't change the height of something, then gravity did no work on it. So if you think it in terms of the fields, if you're not moving parallel to the field, you're moving perpendicular to it at all places, then essentially you are you're not changing the height of it, and therefore no work is being done, and that's what a line of equipotential would be. So you could look at this and say, this has potential V1, and this would have potential V2, and you could label it that, and you could look at, well, what's the change in potential here, and figure out how much work it would be to move from V1 to V2, and same thing here, this could be V1, and this one out here could be V2. I'll put it in here so it's a little more visible. And if we needed to move from this inner potential sphere to this outer potential sphere, because I know it looks like a circle, but they're spheres in 3 dimensions, then you would just have to know the difference in this potential, go back up, use that equation from before, and you could figure out how much work had to be done, right? Because we had V is W over Q for the electric fields. And so you could just say, all right, if I know my charge and I know my change in potential, then I could figure out how much work was actually done. So makes that sort of thing a lot easier. Okay? For these equipotential lines, we could actually write out one more little equation that goes from them for electric. VE electric, we could have just KQ over R. Now, the reason this becomes an over R, I mean, I guess I could explain to you outside of class, but it has to go back to something we talked about before. But just remember, this drops down to an over R, not an over R squared dependence anymore. And we would have this equation. And then we could also have the field for this. I can't remember if I wrote this up above yet or not there, but you've got that. And then for gravity, you have something similar where Vg is negative gm over r, because this is only in one direction. It's always in a attractive force. There's no negative here because the positive charges, they can repel, and the negatives can repel. And honestly, ultimately, it's mostly just a convention for how you want to set up the potential. And you can basically just do that over r, again, not r squared, but just an r. And for this, you can have your equipotential here line. I guess I should put a P on it. I didn't put the P on that over here. We're talking about the equipotential line. Would be just MVG. Okay? I think that's all for right now, and we'll see you in the next video.